2212 Lab 2 Charge Tape Revisited. The goal of this lab was to determine the interactions between two pieces of charge tape and predict the charge of the tape and the excess charge on one piece of tape by treating the tapes as having a uniformly distributed charge, whereas in Lab 1 we treated the tapes as point charges. We also simulated these interactions using GlowScript as a line charge. The purpose of this lab was to become familiar with charge distributions and their properties in real life and model the differences between point charge and the charge distributions. The key physics concepts involved in this lab was Newton's second law, which states that the net force in an object is equal to the change of momentum over the change in time. The gravitational force near the Earth's surface says that the gravitational force is proportional to the mass of an object and points in the negative y direction, and is proportional to the gravitational constant g, which is equal to 9.81 meters per second squared. Another key physics concept involved in this lab was the electric field of a uniformly distributed rod, as the tape is assumed to be a uniformly distributed rod of charge, and the observation point is perpendicular to the center of the tape/rod. This equation estimates the charge on one of the tapes, but we note that the other tape is still treated as a point charge. The last key physics concept involved in this lab is the electric force, or Coulomb's law, which states that electric force is proportional to Coulomb's constant and charge strength, with an inverse square relationship to the distance between the charges. It is also equivalent to the product of the observation charge and the net external electrical field at that point. The direction of r is from the source charge to the observation location, and Coulomb's constant is stated below. Some key assumptions for this lab was that the charge is evenly distributed along the tape, so we can model the tapes as a collection of point charges in a line. We also ignore air resistance and state that both tapes has the same amount of charge. The initial conditions for this lab was that the tape had a length of 0.2 meters, a mass of 0.2 grams, the two tapes were separated around 0.025 meters, the system is said to be tape 1, and the surroundings are said to be tape 2. The procedure is the same from Lab 1. We first created U-tapes by placing tapes on top of the table and placing another piece of tape on top of the first one and pulling the top tape off quickly. Then we were observing the interaction between two of these tapes. And then we observed the interaction between the U-tape and another charged plastic object, such as a plastic pen rubbed with wool. Next, we suspended one of these tapes on two objects of equal height, as shown in Figure 4, and we placed another U-tape below the suspended tape and observed the motion of the suspended tape and noting the distance between the tape. From this experiment, we observed that the two U-tapes repelled each other. The interaction between the U-tape and the hand was attraction. The U-tape and the pens also attracted each other. So, since the pen is negatively charged after being rubbed with wool, it transfers electrons from the wool to the pen's surface. So therefore, the U-tape must be positively charged. The interaction between the suspended U-tape and the other U-tape was also repelled. From our computational model, we found that the gravitational force was 0.00196 newtons downwards, whereas the electric force is 0.00196 newtons upwards. The charge of the tape as a uniformly distributed rod is around 2.54 times 10 to the negative 8th coulombs. This is different from Lab 1 since the tape is a collection of point charges. The top tape is treated as a point charge at the observation location. We use the equation for the electric field of a uniformly charged rod to estimate the charge. Here is the code for the lab. We initialize the mass of the tape around 0.0002 kilograms, and we estimate the charge as from Lab 1 we have here and charge from Lab 2 as a line charge, and the distance between the tapes is 0.025 meters. Here, this function calculates the electric field using the formulas that we had, and this function creates a line charge. Next, we initialize both the top tape and the bottom tape as line charges, and we initialize the electric field vector arrow scale as 8 times 10 to the negative 8. Here we calculate the total electric field on the top tape, and at the bottom we calculate the total electric force and the gravitational force and show that they're equal to each other. So when I run the program, the magnitudes will be equal to each other. As you can see, they're both equal to 1.962 times 10 to the negative 3. Overall, we found that the charge of the tape was around 2.54 times 10 to the negative 8 coulombs, and this is based on an estimation and a rough guess and check method to find a charge such that the electric force is equal to the gravitational force. This means that the net force is 0 and the tapes are suspended in the air. Some possible sources of error include inaccurate measurements of tape length and width as well as separation distance. The tapes might not have been held exactly parallel, causing discrepancies in the distance measurement, and errors in estimation and rounding. If we had modeled each tape as a single point charge like in the previous lab, we would have had a different charge value that we have gotten, as shown below. The line charge model has a greater charge than the point charge model by a factor of 2.185 around. And why do these estimates differ? This is likely due to the assumption of the tape as a point charge versus a line charge, since the line charge model considers length of the rod in addition to separation distance. The line charge is probably closer to the real value since it models the charge distribution of the tape more realistically than a point charge, since the tape is more of a rod-like structure than a point charge.